Today I'm here to talk about nonlinear mixed effects modeling in R through the nlmixr package, especially in the terms of pharmacometric modeling. So I'm here on behalf of the whole nlmixr team. My name is Matt Fiddler. I'm the lead developer of the nlmixr project, and Wenping Wang was the first founder, and everybody here on the list is somebody who has been instrumental in bringing forth our vision, which is to develop an R-based open source nonlinear mixed effects modeling package that can compete with commercial pharmacometric tools and is suitable for regulatory submissions. So the question may be, how are you doing with this? So on the next slide, we see that we have a comparison between one of the standard of cares or standard softwares, NOMM. You can see that in this comparison, which was published last year in CPT, we have similar estimates of our parameters, and we have faster runtimes. We also have had one known submission and approval with to the FDA with the nlmixr software. So what am I going to talk about today? First, the model syntax and how you write a model. The goodness of fit plots we'll briefly go over, and how to use that model to do what-if scenarios and simulate with RxODE. So the first is the modeling syntax and how to run nlmixr models. So most people here are familiar with the NOMM control stream. NOMM control streams have things that tell you about the model. In this case, it's a compartmental model. So you have the number of compartments and the parameterization. You have the fixed effect model that's specified in your PK block. You have your random effect model that's specified. You have your error model, and you have your initial values, as well as these estimation methods. This is similar to what you see in an nlmixr type of model. You have your library, your nlmixr library. You then read your data in, and then you have your function. Your function needs to be something that has an INI block and it has a model block. In your INI block, you have initial values for your fixed effects, and you have random values that you use here, as well as your initial values for your random effect model. In your model, you have the relationship between the fixed effects parameters and the random effect parameters, as well as, in this case, linear compartment model, and how it has residual error. Once you have all this in function in R, you use nlmixr on that function with your data and choose an estimation routine to create an nlmixr fit object. So let's drill into some of these components a little bit more specifically. So the first type of component we'll talk about is this initialization block. In the initialization block, we have initial estimates, which can be assigned using the R operator. It can be assigned using the equal operator, and you can do some simple transforms to get the estimates on the right scale. In this case, we're doing log 90 because we know the volume of distribution is about 90. And since we're doing mu referencing, it's on a log scale. So this is very convenient to be able to put that type of information in. And we can also fix parameters with fix and then the parameter that you're fixing. We then have an initial estimate for our additive error on the standard deviation scale, as well as estimates for the variability of all the ADAs. We use the model by syntax, which is the tilde, to indicate that you're going to be modeling the variance here by this 0.1. If you have a full covariance that you're looking at, you can use the pseudocode of adding two different ADAs together, or two different individual components together, and then using the tilde to say model by. And then we have this lower triangular block matrix specified in R with a C. So C, this would be your variability, this would be your covariance, and this would be your variability of your second component, your VC. So stepping away from the INI block, we go to the model block. The model block talks about the relationships between these fixed effects parameters, this random effect parameter, and also the values that we have. With these three values, nlmixr knows this is a linear compartmental model, and then you model the residual error with, again, the model by formula, this tilde, and then you have it to be an additive error with additive SD is what you're estimating here. This linear compartmental model can be solved, and it imputes the types of compartment models that you are looking at based on the parameters in your model. So a simple expansion from what we had before, where we had a one compartment model, we simply add VP and CLD to be able to have a two compartment model. It's pretty simple, it's intuitive, and it probably is doing the right thing. If you want to know exactly what parameters accepts, there is an article on the ODE website here about the model types in this presentation that you can go to. In this case, we also have this linear compartment model, and we have a model by proportional error in this case. So we have model by proportional error and a proportional SD. If you want a more complicated model, in this case, it's not too much more complicated. In fact, it's the same model, but using ODEs. Here, we would use the ODEs in Leibniz notation. So you have D, DT, and your compartment name, and have DDT as your second compartment name. So this would be an oral absorption and basic linear elimination. From there, we calculate the concentration in the plasma compartment by the central amount divided by your volume distribution. And then last, we put the central compartment or this peripheral concentration being modeled by disproportional error, just like we did before, same type of syntax. We have CP modeled by proportional error with a proportional SD being estimated. Sometimes you may want to add bioavailability and lag time to the model. This can also be done pretty simply. All these are basically attributes of doses. So what you do to do that is you do absorption lag of your depot and then put the parameter estimating F of your depot and put the parameter estimating. You can also do rate and duration for the model duration and rate types of events. These are all standard events using the typical modeling structure that's supported by NOC. So you may want to double check your models to see if everything is there, if it has what it inferred the right model is, what it inferred about the referencing, what it inferred about the covariates. So one way to do that is to first evaluate the model, and then you check how the model is parsed by using nlmixr one compartment, for instance. So this is our one compartment model. It tells you how it parsed. It tells you it was a one compartment model with first order absorption in terms of CL. Then it puts out the fixed effects and the random effects, and it has a little brief description of the model. This way you can see information about how the model is working in nlmixr. Once you have that model working and it's specifying the things you think it should be specifying, you can then use your data, a non-mem data set, and use this nlmixr function to run the model. You have nlmixr, the function name, the data, and the estimation routine. SAEM or NLME, FOCI are common types of things you might want to have in here. You also have this table control where you're looking at, say, conditional weight residuals or MPDEs that you can add to each of those types of objects. When you're looking at this on the R console, it will give you some information about the nlmixr fit. So you have nlmixr of SAEM as the objective function, the AIC has a time it took to set up those things and to optimize, as well as the population parameter table. And in this case, you have the labels you got from your model. You have your model-based estimate, and then since we typically are looking at log transform values with referencing, we want to see what the actual value is on non-transform space. So what we have here is the non-transform value as well as a 95% confidence interval. The next thing we have in the table is the degree of between subject variability, and that's expressed as %CV or a standard deviation. %CV is for the log normally distributed populations. Last thing we have in this table is the shrinkage percentage, and this is based on SD shrinkage because there's also a variance shrinkage, which you can access if you would like by the shrinkage table here. So you do fit $shrink and it will give you that information. This also gives you a little bit more information about what's available in this fit object. You can look at the full between subject variability covariance by fit $omega, or the correlation matrix fit $omega R, where the diagonals are the SDs of your correlation matrix. It also tells you the covariance matrix type, which in this case was FIM. Linear FIM is the current best for SAM and is typically what you would see. The actual fit object is a data table, a data frame. So because it's a data frame, you can do everything you would like to with data table or dplyr or even ggplot directly without having to modify it. We talked a little bit about the residual error models that we were using. We've looked briefly at additive and we looked at proportional. We also have an additive plus proportional, and there's two different types that are supported in nlmixr. There's one that is typically used where you have the additive component and the proportional component. Both of those are squared and you take the square root of all of it to get the standard deviation. Whereas the second one is you just add the two and you don't take the square root. There's no squared here. So the one that's typically used in this default is this squared piece, or the combined two is what we call it, just like the same terminology you have in Model X. The next type of error we have is this log normal error. And the log normal error is actually on the same scale as the additive and proportional because it uses dynamic transform of both sides to get the objective function on the same normal scale, which means that this objective function can be compared to the additive proportional or the additive plus proportional to see what the best objective function is comparing all three error models. Or you can also add a power model, additive plus power, Box-Cox transformation of both sides, Yo-Johnson transformation of both sides, and in SAM you can use Bernoulli and Poisson. If you're using a joint PK-PD model, you can model each PK endpoint and each PD endpoint using this tilde operator to say that you're looking at both of them. And then you can actually add some specifying components with a bracket if you want to be more specific. One really brief excursion is covariates. Typically, we can add many types of covariates, especially in FOCEI. SAEM prefers to have what's called new reference covariates. In this case, it's what we have here. We have our population parameter, we have our random parameter, and our covariate should be a linear combination of something in your data set and estimate. So if you were looking at something like weight over 70 raised to a power, which is typically what we have for the allometric scaling, we would change this to be log weight divided by 70 to make it so it falls into this type of category. This is done for you in the new covariate search auto, which will do stepwise covariate model building and should be released with the next version of nlmixr. Once you have a model, you have the covariates, and it's looking okay, you might want to do a really quick look at your data to see what's there and see what the goodness of fits are. You can do that with a plot, which will produce trace plots, DV versus pred or IPRED, residuals, and individual plots. All of these are just a quick look. If you want more granularity, you can use expose, or as we're going to be using in this session, the ggpmx. So once you have the model, the other thing you might want to do is see what happens with different types of scenarios. For instance, you've run the model, you might want to have BID dosing as opposed to the QD dosing that is typically done. So I'm going to talk about two different types of simulations here, both of them multi-subject and with or without uncertainty. So really quick, nlmixr is powered by RxODE. It solves the ODEs, and those ODEs then estimate the parameters in nlmixr. So when we're doing simulations, we have to use RxODE or even compatible events. So what we typically do is we specify these events in the new event table. One way to do that is through the event table or create an event table here. So in this case, we would have ET amount would be basically a non-mem amount of or a dose of 1,000 units. And then we might also want to add additional dosing and II dosing so you can get this type of a framework. So here we have the two different styles of adding sampling and dosing within RxODE. We have the add sampling function, which can be used outside the function or the event table, or you can use a $sign to access it. You can also add dosing. So you'd have add dosing function, and then you have a dose, number of doses, the dosing interval, and how it's dosed to. This is all also done with the ET function. So ET would be adding the sampling times or adding the non-mem compatible items to it. And here's an example where you can read a dosing table for this BID dose. Well, actually, it's BID plus another dose at 24 hours. So we have this event table with milligrams as units and time units of hours. We add the dosing, and then we put 10 doses at a BID dosing, and at a dose of 20,000, you have 5 doses at an interval of 24. So it's easy to add doses and make complex dosing regimens based on this. So going back to nlmixr, we now know what we need to do to create a dosing table and an event table. So we have nlmixr. The ODE models are already specified. So when we take an event table, we would just put a dose. In this case, we're changing QD dosing to BID dosing. So we're just adding 2 doses, and the dosing interval is 12. Then we add sampling to see what's going to be happening in that particular case. The easiest way is to simulate with no uncertainty in your fixed parameter estimates and your omega parameter and your sigma parameter estimates. So in that case, you could have, say, 300 subjects or 300 times 300. So we're going to do this because we're going to try to keep this number of subjects in between the 2 examples. So in this case, I simulate that and use that BID object as a solved RxOD object with this fit as a nlmixr object, the new event table, and then the new subjects. With this fit, you can see it's an RxOD solved object, which is similar to an nlmixr solved object. It's actually a data frame that you can do certain things and extract certain pieces from. One thing you can extract is the parameters, this BID $sign parameters, for instance. When you summarize it, you can see that these TKA, TV, and TCL have the exact same value throughout. There is no uncertainty in these parameters. So you can say this is a simulation without uncertainty in the fixed effects parameter estimates. Simply plot and adding Y labels and X labels will give you this sort of plot, which shows you the confidence you have in your prediction. This would be your mean level, and this would be your 5th and 95th percentiles, and how it's behaving with this Theophylline example. If you want to simulate with uncertainty in not just your individual values, but also the fixed values and the between subject variabilities, it would be simple to add it. You have the number of subjects would be 300, like for instance, 300 subjects per clinical trial, and you have 300, say, studies or clinical trials. Because you have 300 of those clinical trials, 300 different samplings of your fixed effect parameters will be performed. So that's just one simple change, and it changes your output very substantially. You can see with that same BID object, the population parameters in fact change, and you can see that they're not the same throughout. You can also look at the omegas change. You can see that the omegas have different values for the whole omega matrix based on each individual study that it's sampled from. Each of them are scaled from the inverse Wishart distribution to try to figure out the uncertainty in that omega matrix. Similar, we have the sigma list that has one particular observation here for the omega matrix, and another here, and another here. Basically, same thing. You're simulating from the inverse Wishart distribution based on the degrees of freedom or the number of observations. When you look at the simulation, we're using the same code, plot the BID. You can see there's a little bit of a higher absorption variability when we add this uncertainty into what you're looking at. So we've talked about how models are specified. We've talked about how to run models. And once we have the model, we can goodness if it's a plot function. We can also do simulation from that. Why I just really want to briefly touch on some of the new features that are coming in the nlmixr and the RxODE. One thing that you can talk about is they have custom likelihoods for censoring. So you have censoring support, similar to what they have in Monolix. They have a censoring column and a limit column, and it tells you whether or not your observations are below the limit of quantitation, above the limit of quantitation. We also have the ability to model between subject variabilities for model-based dosing in FOCI, so like F lag time. One of the big things that people have wanted and is a big effort is we don't have any more dependence on Python. We changed it in favor of a C-based symbolic engine called SimEngine. We use the advanced solutions now for common PK models, which are the same solutions that NOMM uses. And we use fast radix sort for internal sorting, which is the same sorting engine that data table uses. And then we allow compartments to be compared directly by simple names. And last, and also important, is the ability to add time-varying covariates in SAEM. You can always go to our resources, which is nlmixr development. We can also always go to the nlmixr.org to see what our documentation is. And what it is for ArcSODE is also similar. It's under ArcSODE. We have our open course material and cheat sheets and posters all published in the publications here. We have a handle on Twitter, and we have a